title. May I introduce myself? I'm a statistician. I'm not a pharmacologist, I'm a toxicologist, I'm a statistician. But of course, pharmacologists and toxicologists also use statistics. And there are a lot of possibilities of misuse of statistics. I will finish my talk with how to lie with statistics. And I want to point out one topic which is possible to make misuse of statistics. And you also know that statistical testing and statistical significance is a very common use, and many researchers are happy when they have a significant outcome and they present the significance like a trophy. And to say open p-values are often missing the trick. Now I want to show you the principle of a statistical test, just the idea what the computation of a statistical test is. We start with something which we call null hypothesis. That means there is completely no effect in the data. And under these assumptions, no effect in the data, we compute a probability. And the probability is computed that the observed data, the more extent data, originate from random effects. And if this probability is rather small, less than number we call level of significance, then we don't believe that this assumption is true. We say the test is significant, and as a consequence we say that the null hypothesis is wrong. And that's the principal idea of a statistical test, and I guess most of you, or maybe all of you, have used such p-values and such statistical tests. Now, the meaning of a p-value. It is in the notation of mathematics, the p-value is a probability, the probability that the test will be significant under the assumption the null hypothesis is right. So in case there is no effect in the data, then we have the probability that the test is significant. And if this p-value is low, let's just say lower than 5% or lower than 1%, then we say the test is significant. So if you take random numbers, and with random numbers we have definitely no effect in the data, and you test random numbers with the 5% level of significance, then you get the probability that you will get a significant result is 5%. So here you can see if you use random numbers data, definitely no effect. When you make a test, then the probability that the test is significant is this level of significance you have selected for your work. And now I want to make with you an experiment in our minds. Let us take a random number generator, that's a computer program today. It's not a dice or not a coin, it's a computer program today. And he gives us 10 times data for, an example, 2 groups. And for each pair of groups, we make a statistical test and we select 5% level of significance. And how many significance results we expect? If we have one pair of groups, then we expect the 5% we have already got. And now if you make 100, you take 100 times the many, so we expect 5 statistical significance. Or if you make 1,000 statistical tests, we expect 50 significance. And because we make these tests all on random numbers, all the significances are false. And the conclusion is, the more you test, the more you get significance, and you get more false, wrongly significant outcomes. And now I want to talk with you the number of possible tests. How many tests are possible in a given data set? And we assume that the data set has V variables, has G groups, and they are observed at T time points. And you can compare each group with each other group. If you have 3 groups, you can compare 3 against the other 2, and because the comparison of group A to group B, the comparison of group B to group A is the same, so you have only half of this. The same is true for time points. If you have 4 time points, you can compare time point 1 with the 3 others and so on. And this can be done for each of the variables, and if you add up these 2's and simplify a little bit, you get these formulas. In total, in a data set, you can have this number of pairwise comparisons. I restrict myself on pairwise comparison. You can make more comparisons, but they are more complicated, and the computing here would be more complicated. So I simplify it. You could also compare group 1 and 2 together, group A and group B together against group C. So this is not a pairwise comparison. This is how we did here to make things simple. And okay. Let's make an example for the number of possible tests. That's a very simple study in a hospital. You have 18 variables. You can read these variables, but this is not so important. You have males and females, and you have younger and older people. So you have 2 by 2 groups, young females and old men and so on. And let me say you have 2 time points, admission and before discharge. So this is a very simple and small data set. But the number of possible tests, exactly the number of pairwise comparisons, is this here. That's a formula you had already. And now you put in the numbers, and then you come with 288 tests. And this is not too small. That's rather low. And it's really a small data set. Most data sets we have to analyze are much larger than this one. And also, and even in this small data set, you could have nearly 300 possible tests. And it's easy, you see that's the 18 variables, that's the 4 groups, the 2 time points, and so on. And now we say how many tests, and look, for each comparison, you can make a statistical test, and you have now 280 pairwise comparisons. You can make so many tests. Let's again assume a level of significance of 5% for all tests, and we still have the idea that the numbers, the data set comes from a random number generators, so we definitely know nothing is in, no effect is in. But we expect 228 multiplied by 5% of level of significance, 14, a little bit more, about 14 significant tests. And all these results are wrong because the data come from a random number generator, so we definitely know there's nothing in, no effect at all is real. And so you can see that in a rather small set of data, you have several significant results. And of course, nobody will actually compute all these tests. It is not so important if the test is already computed. Often you look first on the descriptive statistics, you look on frequencies, you look on means or medians, or you look on the usual descriptive statistics. And if you see the difference between the groups is rather small, of course you will be too lazy, and I will be too lazy to compute the test. But actually, you do you don't compute it, but from the idea we have, it is done. Because you select, you save superfluous, you save work which is not necessary. If you see from descriptive statistics, if you see from the frequencies, if you see from the means that the difference is rather small, you will not compute it. But in case it would have been a serious difference in means or in frequencies also, you would have computed the test. So it is not important if you have actually computed the test. Relevant is only the number of tests which were possible. Nobody made no work which makes no sense. Now I want to come a more serious example. Maybe you will know the National Toxicology Program of the United States. I was asked from a colleague of you, from a toxicologist, whether the results of these tests, what I have to see, what I would commend this program, or this technical report on Ginkgo biloba, what it is. And in this report on Ginkgo biloba of the US National Toxicology Program, there are 4 studies reported, and I take only one of these 4 studies to make things easier. I take the first one, 3-month study on rats. There were 10 males and 10 females rat, and they were administered no Ginkgo or 62.5 and so on. That's the doses of Ginkgo per kilogram body weight, and it was fed to the rats for 5 days, and 5 days a week, and for 14 weeks. So this is a very standard experiment in toxicology, understood. And at the end of the experiment, several organs, or maybe all organs, were investigated macroscopically and microscopically. So this is a classical toxicological screening program. And how many tests are possible in this program? We have 5 dose groups and a control group. So we have 5 pairwise comparison. Dose A to control, dose B to control. We have females and male rats. We have about 10 organs. I just make it roughly, not exactly. And we have about 10 typical findings. Here are some examples. So the number of possible tests is 6 groups, multiplied by 2 up to 6 groups. We have 10 locations. We have about 10 possible findings. So totally we have 1,000 possible pairwise comparisons. And thus, of course, we have 1,200 possible tests. Remember, in the example I gave before, we had only 288. Now we have much more. And again, of course, not all these tests were computed, but if there's a promising difference between groups, then of course it is tested. So you look on the data, you select the tests which are, you have a chance to get significant results, you have a promising statistical results, and then you make the test. And how many significant tests do we expect? Again, under the assumption that we use a random number generator. That means that null hypothesis is valid for all. Of course, I know that they do not use random numbers, but I assume in case it would have been random numbers, how many false significance, wrongly significant tests we expect. And it's simple to calculate. We use again a 5% level of significance, so we have 1,200 tests. This level of significance, we expect 60 wrongly significant tests under the assumption that the data come from random number generator, that there's no effect at all. And in the report, 33 significant results were reported. So we can see we expect 60 wrongly significant results. Actually, we have observed 33. So you will understand that I conclude that these significant results are not a statistical proof, they are just newly generated hypotheses. And this is an important point. Sometimes statistical testing makes a new, generates a new hypothesis, and sometimes it is a statistical proof. And now I want to show you the difference between the hypothesis generation and the hypothesis confirmation. In experimental research, we have 2 very separate steps. The first step is hypothesis generation. We have a screening investigation, we have a survey, we have a result of data mining, and so on and so on. And then you get, you make a test on these things, and if a statistical test is significant, then you have a precise hypothesis generated. And this is what we call exploratory testing. And this is also called data snooping or data mining or screening and so on. And the technical report on Ginkgo biloba of the National Toxicology Programs is, in my opinion, hypothesis generation. And the idea is, or the result is, that you have really important and precise hypotheses. If you have a precise hypothesis, then you can start hypothesis confirmation, where first the hypothesis is established, you make a specific and controlled trial on this, and then you get specific data, and then you make a statistical test, and now you have a confirmative testing, and in case you have now a significance, this hypothesis is a statistical proof. And please, that is my message I want you to understand. If you have a statistical significance, you should know, is this significance producing a hypothesis, or is it confirming a hypothesis? And this is a serious difference. And now I want to say, what are the prerequisites for confirmative interpretation of significance? I say interpretation because it's always a significance. But this distance, the difference is, how do you interpret this? And the prerequisite to allow a confirmative interpretation are here listed. First, and this is the most important thing, you have to, the hypothesis has to be established beforehand. We say a priori, that's Latin, and means before your experiences beforehand or something like this. As we like this word a priori because it's a specific term, but it means just beforehand. Not full of problems is that the level of significance has to be established beforehand. You cannot look on the p-value and say the p-value is 3.5%, and then I will take the level of significance of 5%. In case it would be less than 1%, it would have changed and take the level of significance of 1%. So the level of significance has to be established beforehand. But this is not so serious problem. This is a serious problem. And most important is you need new data for the confirmative testing. The data, the hypothesis generation and the hypothesis confirmation must be on independent, on new data. You must have two sets of data. And in case you do more than one statistical test in the confirmation, you need an adjustment for multiple testing, and there are certain procedures. This is only one of this. And if one of or more of these prerequisites are not fulfilled, then the significance is exploratory. Then a hypothesis generated. So please remember, you need 4 steps and 4 prerequisites to allow for a confirmative interpretation of significance. Otherwise, it is exploratory. And if you go back to the National Toxicology Program with a technical report on Ginkgo, you will see that this was not done. This was done, of course, and it's the same data, it's only one set of data, or 2 sets of data. And this was also not performed. So it's 3 or 4 prerequisites for confirmative testing are not fulfilled in the Ginkgo biloba report of the National Toxicology Program. And therefore, I argue that this is not confirmative, this is only exploratory, and therefore hypothesis generating, not hypothesis confirmation. It doesn't matter what type of study you have. If you make clinical study, animal research, cell cultures, if you have a parallel group or crossover design, of the time of the outcome variable and the statistical test you use, that's all irrelevant. It's not relevant for the decision between exploratory and confirmative statistical testing. And I'm coming to my end. What should you take home from my paper? If you are told that something is significant, you should. If you are told that something is significant, if there's a small p-value presented, you should make clear if it is significant is explorative and generates a hypothesis, Or is confirmative and is a statistical proof for beforehand established hypothesis. There's another important rule for interpreting significant p-values, which are not topic of my paper. So we have two rules. One is you should make clear if the significance is exploratory or confirmative, and you should never interpret p-value without descriptive statistics. Descriptive statistics is the main point, and p-values are just things to be added. But this was not the topic of my presentation. But I want to mention it because I think it's also. In the beginning, I told you that there are several possibilities to lie with statistics. And now you have learned one out of several capabilities to learn with statistics. And if you have learned this, that's fine. And that was the purpose of my presentation. And I thank you for your audience.
Any questions to Dr. Gaus?
I have some references here. This is very new, and it's very similar to my talk I did here, and it was in June, it was published in June this year, so it's present.
If there are no questions to Dr. Gaus, then thank you very much for your presentation.
If you have no questions, and if you have some more time, Mr. Chairman, I can tell you a story about benzodiazepine, as it's more a joke than a scientific result. But if you want to listen, I can give you a statistical problem.
Okay.
Okay, somebody has a serious diarrhea, and all his feces go into his trousers. He consults a physician, and the physician prescribes a benzodiazepine. And the patient tells this story to a friend, and this is a real friend. And the friend thinks, a benzodiazepine is treatment of diarrhea. This is odd. This is strange. And who would understand that? And then he asks the patient, does it help? Are you now continent? No, says the patient. Still, all my feces go into the trousers, but I don't mind. And now, that was the joke. And now there's the serious compound. If you use quality of life as outcome variable, then benzodiazepine is effective in diarrhea. And of course you will understand that this is just an example how to lie with statistics, but you have to think of that and also. Okay? You want to have another joke?
But thank you for now, Dr. Gaus.
Okay.
Appreciate it.